Hello, and welcome to this final lecture of the series on quantum gated logics. And now we will finally look at a combination of what we have learned so far, and that is a hybrid classical quantum system. So up until now, we have learned about the single qubit, multiple qubit, a single gate acting on single qubit, but multiple gated operation on combination of qubit or multiple qubit as well. But there is another class which has much more practical and commercial value that we should look into. Now, before we delve deeper, what we have seen so far about the single qubit gates like X, the Hadamard, the Z gates, etc., they are quite useful, but their purposes are also being very limited. And they are not the only gate. So if you look at this list provided below, you will find many other gates which has one function or the other and bring in value during the calculation. However, the problem with single qubit gates is that their operational capability is very limited, and that's why for much more complex practical application, we would have to consider something else, what we called as parameterized quantum gates. Now, we already know about the single qubit, how it is described. It is constrained by its amplitude, where the square of amplitude must add up to 1. We have also seen the Z gate and the application of it, and so forth. We will not delve deeper into this now. If you wanna know more about this, please do watch previous video lectures on this topic. But the idea to derive here is that their capability is quite limited. And what they do basically is that on the Bloch sphere, that is also something we have seen in the previous lectures, is that they have only a specific rotation capability. So these gates do not traverse the whole Bloch sphere, but only in a certain direction, only up to certain capability points. So this has a very limited operational benefits that we can accrue out of these gates. Now we can enhance this by means of uh, having gates which can change its behavior based on what is the input that we are providing to it, and that is called as the parameterized gate. You can control it by a parameter. For example, we look here that there is this parameterized gate ry with theta as a parameter, and this is something to be noted that you have to define the parameter before, so it is not on the fly or on the run kind of specification. And what happens that this particular gate ry of theta rotates on the y-axis of the Bloch sphere. Now, any rotation around the y-axis of the Bloch sphere can also be conceptualized in form of a matrix. So for example, this gate of ry of theta can be written in a matrix format in terms of the angle parameter that it is making with the given axis, which we called as theta, which is controlling the rotation. And then you can define the matrix as cos theta by 2 minus sine theta by 2, sine theta by 2, and cos theta by 2. Now, let's begin by giving that this gate is acting on an input qubit, which has a state of 0, And you can literally play the same steps that we have seen many a times of multiplying a matrix with a vector representation of an input qubit 1 0 in this case, and what you will find is an output which is cos theta by 2 to a state of 0 plus sine theta by 2 to a state of 1. So that means it is creating a superposition after applying the matrix to the vector. Now, how shall we change the values of this particular output? And that is driven by the parameter theta, as we have said before. So for instance, if you now take theta as in 0, that there is no angle between the y-axis and this parameter, you could say put theta as 0, which will then give cos theta as 0, which is 1, and sine theta as 0, which is 0, and then you will end up only having a 0 qubit state. You can also have, for example, theta as marked as 180 degrees or pi, and in this case you will have cos theta by 2, which is cos 90, which is 0, and then we have sine theta by 2 sine 90, which is 1, and there you end up getting one state as output. You can play with these parameters as many times and with as many values and discrete values as possible. So this becomes quite handy. Now, this has a very important application in terms of using this parameter-based circuit to basically gain or learn about optimization. So what we see here, for example, a simple a classical circuit where then input is coming, going through a gate which is being measured, and now we want to use this to basically optimize our circuit. It could be that the optimization problem is how far we are from the expected value compared to what is the actual value that we have received out of the circuit. Now, in this case, what we can do is like the concept which is also used in other fields like neural nets, where the idea is to minimize the cost function, and then what you can do that you go through this iteratively to calculate the cost such a way that how many shots have been fired, like how many iteration of this circuit has been run, minus the count of one that we actually got, because that is what will give us how many times it is far off from one and what is the cost of that iteration, which is something that we can then optimize to bring it as closer it to one, so that reducing minimizing the cost function and then calculating the overall cost. This can be implemented in many different ways. For example, Kobala optimizer is one of them, without getting into the details of it, but there are many other optimizer circuit that you can use in such a configuration to calculate your optimized value. So this is just an example of how it can be, the quantum gates can be very multifaceted in terms of controlling it by parameter, and you do not always have to use the simple gates of X, Y, and Hadamard. They have their value, but once you get into much more complex scenarios, parameterized and a combination with single qubit or a multiple qubit gates will make it much more easier for you to handle the situation. So I'll stop here. Thank you very much for listening. This completes the series on quantum gate logic. I hope you enjoyed it, and I hope to see you in the next video. Thank you very much.